Okay. Efficiently live streaming. Perfect. Uh, and share. Okay. We're waiting to see who else is in. Um, da, da, da.
Excuse me. Just I
Yes.
want to ask you about the presentation for the final project, okay,
Yes.
and the
Go ahead.
submission itself. Uh, Is it possible?
Oh, yes. Somebody told me I forgot to add the the assignment submission thing, right?
Yeah, if you don't mind, like, is it possible to submit the presentation with like a voice recording, or you need it like to be present like during
No,
that
I
day?
want it to be presented with slides and everything.
Yeah, thank you.
Uh, term project submission. Uh, and when is the, let me check something. Uh, December 8th. Oh, we have our other friends arrived, so we'll be starting in 2 minutes. See if someone else joins us. I should have kept it here. You were asking a question. I put the submission. You okay? You are wondering if it was audio? No, it needs to be. We're going to do a presentation together. So in 2 weeks' time, right? The Is that correct? When is the last session? Next week or the following one? The following one, correct?
Yeah.
Okay. So then we'll have the presentations and the due date for the term paper is the December 8th. Okay. Let's begin. Okay, so we left off last time, I believe, on talking about the geometry creation tools, and I showed you the slides on how we use LibreCAD to do to achieve it. So let's go and look at it today. I have LibreCAD here. Nope. Uh, is it not? Let me check my scene switcher. Uh, uh, okay. So I have here insert a copy of LibreCAD, which we talked about last time. And we're going to use it today to create a geometry, and we'll see the basics of how we would use it. So I will create some layers here. You use it basically like AutoCAD. I will create a background. I'm going to trace over a background image, but obviously you may have your your dam specified with different geometries. I just checked online a random dam geometry. And today we're going to trace over. So I'm just creating first a background image layer in which I will insert the file. You can still hear me, right, guys? Um, I hope silence means yes, but let me. Oh, oh, okay. I see yes on chat. Perfect. Don't hesitate to speak audibly if you have a question and I'm not seeing the chat messages, okay? Don't you won't be interrupting. I would expect you to. I'd rather you ask me through audio than my not seeing the message, okay? And it does keep connection with the class. It's the worst thing is these online lectures are not my first choice because they can be very difficult to perform when there is nobody. You feel that you're talking to yourself, basically. Uh, so uh, we will insert an image. Oh, I should have started it in a wine window. Yes. Oh, well, too late. So let me find the file specifically, and I will come back. Uh, just So I went to File, Import. Okay, so I just imported through the menu, import. So if I go to File, there's a import, insert image, and I inserted the image, which is not necessarily to the scale that I want. I don't really have a true scale for this, so we're gonna make up uh, a size. What do you want the height of the dam part to be? How tall is our dam going to be? We're gonna use that as a size. But I want your contribution. Don't be shy. Don't be shy.
20
I only
meter?
eat, huh?
20 meter is enough?
20-meter height? That seems a bit excessive. Maybe I would go a little bit lower. Say 5-meter high for
Yeah.
the dam itself. And I think that would be a good potential height. Let's see. Okay, so we will set this. Okay. So I have established here. Oops. I see my window has displaced. Just give me a sec so that I fix that. There you go. That looks better. So we will be working with a calculator sometimes to do our scaling. So I want to go through the full workflow of using inserting an image, and basically. So here is uh, the worst case where you would be using um, say so something scanned from a paper or so to get the oops. It's not what I wanted to move. I wanted to move this one. No, no. Reference point will be there. Target point will be there. There you go. So I just wanted to move that line. I just want to use it scaling reference. So that is going to be 5 meters. Okay, and I can use the command dist here to show me what the actual measurement is. I will get rid of see the snap here at the base. We have the snap values. I will just snap to the endpoint of the line. And now I see that the length is 104. Okay, so I want that to be 5. So I will use my calculator and say my scaling factor will be 5 divided by 104. Okay, so this is my new scaling factor. And so now I will have I will scale. I select the object I want to scale, or maybe I should select, oops, I don't, yes, I want to select that too. So I want to select everything and scale. Reference point. um, will be the bottom corner. So you notice these three are to fix the restrict horizontal, restrict vertical, restrict orthogonal. Now I will keep my corner to the same place, delete the original, and choose my scaling factor. Uh, Oops, they did not select the image. Sorry. Undo. Let me see why it's not selecting the image actually. There you go. Let me save it. I don't see the image right now, which is a concern. I don't know if this version has an issue. Let me double check something. I know. Otherwise, one thing we can do, yeah, when we're having trouble like this, we don't let that equip our style. Okay. What I will have is a tracing layer. We will first trace and then we can scale after if the image is causing trouble. That will be easier. We will make it in red. No, we will make it in yeah, cyan. Okay. This is only for tracing, and so I will just trace the various lines. And I make sure that I have free access. So I will so I made one line. We will make another line for the second layer. We just want to be uh, so we take a new line from here, horizontal. Okay. And now we want to build the dam itself. So how are we going to do it? Just as we usually do. So I will use, instead of free point, I will make any closest point so we can go and make sure we're on the line. And then make a new line, 2 points. I use my toolbar there and we can, oops, did I forget? Yes. line without restriction. And I want to be on the nearest point, snap on entity. That's what I'm looking for. Up to here, restrict horizontally, up to here. Snap on entity up to here. Okay. And now I will have the core outlined again as I'm just going for the points right now. It will not be an exact geometry. It's all that we need right now. So okay. So now we restrict horizontally to go here, remove the restriction and come here. Um, we can also have another horizontal one starting here somewhere. And I will define our full domain boundary. And the last thing we need to identify is our our phreatic, well, the level of water that sets the boundary condition upstream. We will click it there. And now we restrict horizontally until we get there. Okay, so the basic points have been drawn. Basic geometry. I will delete the image right now because this is what I really wanted. And I want to convert everything and scale it now. Reference point will be that point. And we have our scaling. We will move reference point will go to 0, 0. Okay, so now let's check the distance. Distance, we check end to end and it's 5. So that is perfect. We have the dimensions that we want. So this is just my tracing layer. I will create zone outlines. Okay, and that one I will just give it a color. Okay, for now to make it easy. I want to make simple complete line outlines to avoid. Let me first make these. as even as possible. Uh, but let's make a vertical line here. Use the command trim. Okay, and then we go to this. Okay, I believe that they're all the same length now. So that if I make lines, I will make lines from, oops. Okay, let's make another vertical line here because I believe, yeah. And trim, I just want to, okay. I had forgotten to do a proper trimming. I will also put, again, I forgot to trim again. So vertical line there, trim, select entity, limiting entity and trim. Okay. Now I trace again, but this time I go to all my and I complete. So we can hide the layer. Uh, and now what we must do is look at the uh, oop, not what I wanted to do. So if we have a quick look at our so we have our shell, we'll have the coarser materials. Foundation soil 1, foundation soil 2 should have the lowest hydraulic conductivity. So shell FS1, FS2, and 4. Okay? So it's a simple enough profile, but all we need to show the basis of the technique right now. So we will have shell, which will make yellow. Orange, brown, and cyan. Gotcha. So shell. I will change the name. I will call them all layer or yeah. Material shell. And now material foundation soil 1. Material foundation soil 2. Oh, did that. Okay, that should be foundation soil one. Uh, Material foundation soil two. And we had material four. Dark cyan. Okay. So I will mostly use those just for, so now I will use the command hatch. Okay. Um, I will use the solid hatch. So for the core, I select the bounding lines for the core. I am done. Oops. Okay. We will select the shell. So we go, for now, I will turn off material core. So there's no accident when selecting. Okay, so this one will be material shell. Okay. We did material core, material shell, foundation soil one. So foundation soil one will be made by these segments. Okay, we have a little problem here. We can do it in two pieces. That's all right. Okay. And foundation soil two. We will select its components also. Okay, so now I turn back on the various layers. Okay, so we have the the whole dam properties. Oopsies. We're gonna have some issues here. I will redo this one and that one. Uh, Vertical. We should make sure that we're here. Use the command trim to this edge, trim, trim. And now we trace two lines. Okay. So material, foundation material one. I will again turn off the core and shell. Hatch. Okay. And material, foundation material two. All right. Turn all the material layers. Okay. So now is when we are ready to do the export. I go to File, Export, Export as Image. You don't see. Let me make sure that I add this window. so that you can see it. Just give me 1 second. uh, Export image. Oh. Oh, this is what we wanted to see. So I export, and here it's important to have it as XPM. Right? There's two that look, it's X bitmap and X pixel map. Pixel map is the one we want. I will just keep it in its proper place as an image for today's work. It would be and now we have export option. Um, yeah, so we have the image export options. Uh, so we see it's going to be 56 width by height 29. So let's make it colored. So the height is effectively 7.4. And the width is effectively oh, sorry. So the distance is 28. So 28 for the distance. And for the height, we had for the horizontal distance and the height, the width, 28. And 7.4. So let me export this image again. 7 point. So there is a difference in scale here. Correct, because let me just our true ratio of the image is 7.4 over 28.26 or 3.7 times, and here we have 1.9. Mhm. Yeah, so we have about a factor of two scaled. And so if we want to go 26 times 2, 7.4 is 15, right? So the height, if we want to keep it at half, 7.5, it would be 15. 56, 28 to 56. Yeah, so every half meter, basically. We're going to have half a meter in both directions. I prefer to keep the same resolution. We don't have to, we can change our scale, but this is one thing you have to be careful at this juncture, whether it's saving at scale 1 to 1, and it may change the ratio based on the image. Okay, let's see what the image looks like uh, just as a drawing. This one, XPM, right? Oh, did I keep? Sorry. One thing I forgot to do. It's super important. Before we export it as an image, we have to make sure to remove the border. Export. We want to keep our image as clean as possible. We said 15. XPM. Yeah, so that's basically what the image looks like in that file as an image because it has very low resolution. So we may want to increase that resolution because there was very few pixels, right? So let's go and export again. We'll keep the same ratio, I think. So we have 560 or 28. 148. Uh, okay, that looks already much better. Oh, and I forgot to remove the scaling line. Okay, and we can see that I did not have a very horizontal line uh, when we were considering the soil one, but it doesn't matter. I'm not even going to change that. All I want to do is turn that one off. Okay. And now, so this is the image we want to import on the spreadsheet. So we have to go to the spreadsheet and open the file. So I will open that file as spreadsheet. I forgot to. Okay. So this time what we have to do is insert the open the file, but we will open it as a text file. Okay. So um, it has spreadsheet window. Yep. So I go to file, open. I select my file. XPM, damn image XPM. Oops. Sorry. I have to make sure that I open it as open as a text file. Text CSV. So in the file type, select text CSV. And now, if you open it as text CSV, it should show mm, this dialog box. Okay. And now you can open it. You can start, see that these are the different colors. The way it works is static header, it's a character, then it has the rows, the columns, the number of colors, and how many characters per color. And so character A will be color 008080, etc., etc. So the background will be a dot, it's F. So we have imported that. And we have it, actually, can we make it fixed width? No, because we would have to define everything, so forget it. Comma, make sure that text delimiters is there. We will start at what row? We will start at row 9. Okay. So we will start importing at row 9 and bang. We have now a single file. I will transfer it back into this sheet here. Okay, so this is basically the text file that I have imported. Okay, so there's only one cell. Each row is one cell. So it's not very useful for now. Maybe if we define variables just here to to do some processing on our side. I always like to have a variable sheet. We can have the length of the first row will tell us right away. So it counts the characters, 560 characters. So that's the number of columns that we will have. I hope it's not too many. Let me check. XFD. Oh, 16,000. Okay, it's more than we need. Perfect. So now we will transfer those in terms of image. Okay, so we will say, I think it's mid of the character here. I will lock the the column because there's only one column. Um, sorry, column. My current column minus column of A1 plus 1. Okay. And number of character 1. Okay, so it only has one dot. Okay. So it's only one dot. We want to reproduce that. Oops. Wait. Column. Oh, sorry. I want to fix the column, not the row, and I did the opposite. Uh, okay, so now they all move by one because I said column minus column A1, so it's always referencing the first column. I will go to the top there. I want to go to the end. I don't want too many characters. So what I will do is paste special values. Okay. By pasting values, I cannot now go to the end of this. So I know that anything after this is a formula that is just taking up RAM. Okay. So I got rid of those. So these are all formulas. But now one cell is one character. Okay. And I can do that until I go to the same basically row that I have here. So it goes to row 148. Oh, and I'm not sure why we have, why do we have an opening quotation on the last row? That is strange. And we'll have to open the file, but for now, let's keep it like this. It's good enough for our purposes. Okay, so this is the text file, and this is what it looks like when it's What is strange is why we have so much. Oh, it kept. Okay, I see. I changed my my scales incorrectly apparently because the distance was already from a bunch of blank space on the sides. I did not realize it when I opened the file, and I should have. If we go back here, notice how there's so much white space ahead. I thought that it was starting, yeah, that it was starting here. It usually does it. I moved it to 0 for some, but for some reason it saved a lot more. So, um, how to make sure. Uh, Here. Mhm. Let's see if I can. There you go. So, let me see where our boundaries are because see, it's that. Let me remove layer. I don't know why it saves so much more. Okay, let's see if I export as image. I can export as image. Now it does something a bit more. 561. Oh, apparently I accidentally deleted the core. uh, let's see how I did that. Material core. Okay, let's see how it looks now. Okay, yeah, that's much better. This is what I was expecting. So we know it's half a uh, not half a meter because it was 28, became 56, 560. So we get a bit more resolution. Um, so it's basically 5 centimeters per uh it will be 5 centimeter per pixel, right? Okay. So let me re-import the file. Should be faster this time because we did it in the first time already. So I open file. Change the text type to text CSV. Otherwise, it will open it as an image. And once you open it as text CSV, you will have this page. So it's still from row 9. It hasn't changed. I can check here. Okay. And let me remove the sheet. Okay. Uh, and move our copy sheet to the other document. Okay, so we return to our file with the image. And here we must once again, so we control home. Yeah, it's a lot of pixels, so it's taking its time. Sorry about that. I need a better computer, I guess, to play with these things from home. We're gonna delete all these equations. Okay. It's taking so long to respond. I don't even know where I am. Okay. There you go. So I do have the keyboard monitor down at the bottom. If you want to keep track of my actions. I'm not sure where it stopped there when there's clearly stuff below. Well, maybe not. Okay. And so we're going to refer to image. Okay, and we make sure that we lock the column. Paste everywhere. Copy the whole row. Paste only values. By pasting values, we can now go to the end of the row, which is a quick way of finding where the boundary is. Now we can delete that row. Come here, copy. Uh, we were going to 147. And I don't know why I have another. Let me see why. Aha. I accidentally pasted stuff here, which was using up valuable. Ah, yes, it's so much lighter now. So what I will do before I continue, I will convert this. I mean, sometimes what you can do is skip the first row because you may want to recopy the formulas later. But you notice that formulas take time to process. So we're going to copy that, paste it special, and paste it as values. Okay, so I've kept the first row. So if I need to redo the formula for a new image, it will be easy to do. But the rest are all dots. Um, Alternatively, one thing that I could have done, uh, okay, so is replace the dot with something else or a blank or something like that. But we'll get to it eventually. But for now, what we have is a nice image essentially in text format. So we can now have, say, if I insert a sheet that I can call, say, material map. Okay. Uh, Key, and here I could use the character. So I can have material. This was shell for foundation soil 1, foundation soil 2. We can have hydraulic conductivity. In our case, for this problem, we will say that it's always the same. Okay, so I have assigned my material properties here. But you could have the same thing for density. You could prepare a table like this with multiple different properties. Okay, so here I have B, and C. Oops, sorry, that's soil, foundation soil. So this is B and this is C, and core is, let's find the core. I mean, you could do conditional formatting and have these colored too. Uh, okay, here we see the core, which is A. Okay, and core is A. So what will be our material properties for the different materials? Let's just select them quickly. Let's say for the shell, let's say that it's 2 times 3 to the 2. And that's in meter per second. Okay. Uh, um, say that the soil layer 1 will be some type of sand. Uh, let's call it 5 times 10 to the minus 5. Sorry, that should be layer 1. Foundation soil 2, maybe some till material. Let's say times 10 to the minus 8. And our core will be 2 times 10 to the minus 10. Sounds good? Those will be our material properties. Don't hesitate to ask questions, contribute, make comments, so I don't feel that I'm talking to myself all the time. I know it's intimidating to talk when it's online, but it's also very helpful sometimes. Okay, so now the idea is that we create now, we can now create right? Um, the a little table to take in and the and extract the for each row and so on. We can extract the material parameters. Okay, so uh, eh, rows, columns. So columns will be the length of that. Okay. What will be the number of rows? That would be uh, I'm just getting a quick count of the rows and columns. What was the height? Dam height two. Oops, count a offset dam. I want to be 0, 0. Okay, so we have 148 rows, 561 columns. And what was we're looking for the delta uh, delta x and delta y. We said it was uh, um, we had 28 meters. So let's say 0.05 should be right. And that one 7.4, yeah, 0.05. So 5 centimeters is basically the um the spacing that we're using uh in both X and Y. Okay. By making it equal, it will simplify a little bit our the calculations that we have to do. So what were the equations that we needed to do when we wanted to find steady state? We have basically it's a weighted average, right? So let us let's see if we can go back to figure out what we were doing back then. But when we were doing our calculations, so what did we end up having is that the hydraulic head oops, one size. So what was it equal? You recall off the top of your head? Oh, we have to go back to our old files there. Okay, let's see what we had in the previous hydraulic conductivity when we're taking um, it was hydraulic conductivity with uh, 2D with heterogeneous soil, right? It's basically a weighted average of the neighbors, right? Because we're doing a steady state. So so if we have uh, basically when we had the uniform soil, what did we have? It was one half of each neighbor or 1/4 of the neighbor. So it will be kx left times h left, right? Plus kx right times h right plus ky up times h up. uh, plus ky down times h down. And the whole thing divided by, when we went to a steady state, that was basically the problem, correct? Kx plus k, kx left plus kx right plus ky up plus ky down, right? If I go from memory, just on that, that's what we end up having at steady state, which is the problem we're trying to solve right now, correct? So it's basically that weighted average of the neighbors from the previous iteration that we want to achieve in our setup. Okay, so the first thing we need to do is determine the kx and ky for the cells. And then we'll have to remember that we have to go at the nodes to get the full effect of our setup. Okay, so we have the image. Again, this is something that takes time to set up the first time. But once you've set it up, you keep your spreadsheet around and you can just import an image and just expand and adjust the boundary conditions when the thing is ready. Okay? But you can do this on fairly decent sized problems like this. So we have our material map. We have defined our basic delta x and delta y. And because delta x and delta y uh, is constant, and because we're not looking at time dependency right now, we're only looking at relative, so at steady state, so things are always relative. So that's why those equations always ended up basically ignoring the basically ignoring the interval at steady state. Okay, it's because it was equal. One was equal to the other. Otherwise, we would have to take it into account in our geometry. So the first step to do is find the material properties at the nodes, right? um, sorry, at the cell center. And remember that each center of a cell will have to have, so we'll have to have one more row of nodes than we have rows of cells and one more column. And as I said, to make things easy, I just make a fuzzy node kx and node ky so that we don't have to all the time. So that's an average of the four neighbors so that we don't have to do it at each, to check each side in each direction. But the first thing to do is definitely to create now a kx. Kx cell. Okay, that's the true kx. I just call it kx cell because then it's easier to write kx and ky. And we'll do the same thing with ky cell. Okay, so that one will correspond to the pixels. These will correspond to the pixels that we have for the material. There will be one row and one column less than the nodes that we actually need in our analysis. Okay. One thing that I want, so I define here a variable just for the corner called material data. It makes it easier for me to find my variables. But one thing that I want to do as variables go is define material count. And that one will be count A. Uh, sorry, I call a material data. Okay, so add material count uh, count A, so it counts characters. Offset material data. Um, we want to offset by 1 in terms of rows, 0 in terms of columns. We assume we can have up to a maximum of 2,000 materials. We'll never have that many, obviously, and 1. Okay, so that will just give me a count. Sorry, that should be materials count. Okay, so we have 4 materials. That's just a quick way to do it. um, Another thing that we can define here now, once that we have the material count, is material keys, and we can have here an array. So we use the offset command. Material data, we offset it by 1 row because we don't want the headers. It's 0, offset of 0, and then it has material count number of rows and 1 column. So this one, if I were to say material keys, basically material keys just contains the strings of my materials. And that way I can do the same thing. Material AX. This time the offset is 2. Material AY. And the offset, the column offset is 3. Okay, so wherever I am, that's what KX returns. KY returns this column, but uh, okay. So this one is, oh, okay, I made a mistake. That came in handy to show that I had exactly the same, that I had correctly identify KX and KY. Okay, so that way I will just be able to search, so I can match. Say I want a character here, okay? That is going to be one of those. I can say match uh, that character in material keys, and I want an exact match. Okay, it's character 1. If I had A, it would be 2B. Okay, and so I can have index KX, material KX. Okay. And so it gets automatically the KX that corresponds to the character. So if I put this into there, I get just from 1 row. So I can just check the cell and get automatically the KX that corresponds to the point. Okay. Now we're gonna have a problem when we hit that. Okay, and that will get an error So we can always have if is error. Just return an empty string, otherwise return that. Okay. Sounds good? So that's how we're going to populate these two sheets. And then we'll build the geometry based on it. Okay. So we go here, we say match. Call it domain keys. Domain key, DK. So we go to the top value, we say match. DKA1. What was it that we wanted to match? We wanted to match material keys. We wanted an exact match, right? And if it's an error, we wanted that. And if is error that, return empty string, otherwise return that. Okay, and we do that until okay, so we have the beginnings here. I will just copy the last row. Can you tell me why I'm just copying the last row? To check at my finger, so Control Shift and arrows let you go to the end. So I will copy the whole thing, paste special, just the values. Now go back to the end. And now I have identified the end of the row. I delete the rest. And there you go. Okay, so now I have the width. I don't need to worry that I will have too many things. Okay, and if I were to reduce that, now what I will do, except for the first row, again, as usual, I copy and paste special the values. Okay. This is a way to reduce recalculations and save on memory. But if I zoom out, at some point I should see, okay, this is what it looks like. Okay. When you have, you can see just from the shading of the numbers what it is. Obviously, let's zoom in a little bit. Obviously, we could also decide to format, conditional formatting. We can add this one. Let's make it percentile for this time, just so that it changes more colors. And now we should see different colors for different zones just from that coloring. Okay. Does it start to look cool now? So you see we have now our, I will remove Manage format conditional manage. I will remove it now because it's causing, I don't want to do extra computation, but this is how we will do it. Okay. And oh, that was, sorry, I made a mistake here. Can you tell me what mistake I did? This is just the index. This is just the index of, which is okay for the first part of the, to check if there's content, if it's an error message. If it's not an error, what I want is to return the index of material KX, right? And I will repeat. This time, instead of having an index to a value, it will return the actual KX. If I did not make a mistake, obviously. Okay, so now we have the actual hydraulic conductivity in the X direction. Again, I will copy everything except the top line that I keep for repeating the info and paste values. Okay. By saying paste values, you can see that things go much more smoothly and I have actual values in each cell when I go to it. Now I will copy that first row. Make sure have the K with $sign, okay? Let's copy that first row until KY. I will replace here in the formula KX with KY. Copy that on the entire row. Okay, so that we have KY everywhere. And do the same as we did before. Paste. And we paste the values. Okay. So that all we have now are the hydraulic conductivity value for the soil. Okay, so now one thing we'll want to do at some point is have the domain identified. So I will just create a sheet here called domain. And at some point it will become useful. And that one will look at either KX or KY and just count how many data points we have. Okay. um, just Down. There. And obviously, I will just come here and take this line because it's very useful to figure out the end of my domain. So this counts the neighbors. Once you get to so 0 means that I'm not at all in the domain. 1 means that we are at the edge, right? So 4 means we're in the middle of the domain. 3 also means pretty much that all our neighbors are domain. 2 and 1 mean that we are at a boundary condition, however. Okay. So whenever we see 2, we see 1, it's a boundary condition. Here I should have had some edge actually. And this is something I will want to do for my materials because um, okay, so here all of these are on the edge, so I will need to make sure I identify properly my boundaries. Okay, so they are okay. Okay, so now these are all proper boundaries. So 1 is a corner. Um, okay, 2 will be an edge boundary, so only in one direction. 1 will be a corner. 3 and 4 are inside. So 3 is when you have like, yeah, it would have to be a domain like this, but you would have the node in the middle. Even if only 3 of the neighbors are part of the material, it still has an edge above, an edge below, an edge on the right, an edge on the left. So 3 and 4 are nodes that are in the domain. So I'm not sure if I'm making it myself clear. Uh, so what I'm trying to say is that if I have 4 cells like these, right? Since we are counting the nodes, right? If I have 3 neighbors, well, my node is still uh, my node is still that one, right? So if it has 3 neighbors, there's still material, uh, it still has another node above, right? Because there's still a corner of material, so there's still a node on the left as well as a node. Okay. So 3 and 4 are basically the middle of the domain. Now, if there's only two cells, well, there's no more node above, right? Because I've removed that material. And if there's only one cell, then obviously there's only two neighbors and no longer the four neighbors. So that's why that count of domain is very useful, because you can automatically say if you have a boundary and what kind of boundary condition, like if it's above or a corner boundary. So there's a lot of automation that can be done just uh, by counting cells. Okay, so this domain is already node based, while kx and ky are cell based. So that's why I needed to add a column on the edge there. So that empty space so that I could do this little finagling. I suppose I could have done it from the other end too, um, which is something I could think of in the future, actually. Uh, yeah, I'll think about it in the future because it might be more convenient to be able to start from the end. In any event, once we have a domain created like this, um, we can now go and define um, our material properties. Okay? And only if there is basically a node there. So we are going to find the average of the four neighboring nodes. Here you could have also have said if count, otherwise empty. I think that could also work to make it easier to see. Yeah. So when it was 0, okay, so we now only have the neighbors, and you can see the boundary conditions. It's easy to see where you need a boundary condition, right? Okay. 1 and 2 and 1 and 2, and here we'll be able to use that ability later on, by changing. See, this one and this one have a top boundary condition. This one here, that one would be a top left boundary condition. This one is top left, so we can do automatic replacement later on of the domain equation. So we can use this one as a template and replace the index value with an equation or an equation placeholder, and then the appropriate equation. Okay, so that's why it is so useful to have these, because we can do a quick search and replace. Okay, and all our boundaries are already determined. Okay. See how easy it is to identify boundary conditions? You can have the spreadsheet identify boundary conditions for you. Obviously, if you had an internal boundary condition, you would have to go and define it by hand, but usually you should have left that material as a different material empty, and it would have also uh, been able to identify them. So now we're going to insert here. I will call it KX and K. They're not the true ones, but these are at the nodes, right? Those are the fake KX and KY that I assign at the node to make my life easier. Okay, and these are the ones I will use in my calculation. And for this, I will do average. Uh, or I can say if is number, let's go to the domain. Uh, is number, domain A1, average, and I take the four neighbors. Otherwise, it's just empty. And the same way, I take what? Where was? Oh, was I at KY? Okay. Um, except it's not the average of KA domain, it's the average of KYC that I want to do. Okay, 4 cells, 4 neighbors. Again, copy, paste values, except the first row. Okay, so now this is the average of the KY. Okay. And we do the same thing for KX. Copy the equation there, paste it here. It's the same calculation except we take KX. So KX. So here you can see the boundary between soil layers where you have that little seam of blurred hydraulic conductivity. So that's what you would expect. Okay. The boundaries, you expect to see some blurring. Let's see if we find the core somewhere here. It should be close to the core. Core. Oh, there's the core. So you see that blurring at the at the interval, and it's okay. I mean, if anything, it's probably closer to reality in terms of how soil mix at their boundaries. Okay, so this is how we define Kx and Kd. So now we're going to use the domain to have our uh, next and previous sheets. Let's call it next. Again, it's a pseudo steady state, right? Instead of using a matrix, because it's much easier to do it this way, we don't need to define a matrix. Oops, did I just say insert instead of duplicate? I want to duplicate because duplicating gives me the geometry predefined. And do feel free to ask questions, huh? I see everyone so silent. I'm gonna have to request a joke. No? No joke? No yoke? Okay. So now we're almost done. All we need to do really is to define our equations in terms of next and previous. Sounds good? And then we'll have to do a copy and replace. So 4 will be replaced by the general equation. Then I can do within areas, I can do select search and replace, targeted search and replace. Okay. So I can zoom out as much as the computer will let me. Select areas, say here, replace 2 by so and replace 1 by but first we need to define our little equation. But you see, it's just going to be exactly what we did the last time when we did it in 2D with search and replace of the when we did the what was it, the well problem? It's exactly the well problem. Just that we define our equations and then we do a search and replace using these 1, 2s, and 4s as guides for search and replace. Okay, because it has that basic information. The one thing we will need is define the so for the potential seepage phase, we do need to define an elevation head. Okay, so a column where we'll keep the elevation head, and that's all we have to keep in mind for that special boundary condition. But we will define it. So let's start with what it means. So we are on the next sheet, and we will refer to values on the prev sheet, right? So I will zoom in to make things a bit easier to zoom into a full domain cell. Okay, so B103, B103, it keeps things easier for us when we do our definition. Of course, you can always use the row and is everyone aware of the different ways to write formulas in a spreadsheet? Not all spreadsheets allow for this, but most do. Google Docs does not, for instance. Is everyone aware of the, if I go options, oh, options is not in. Let me, um, if I go to options, options dialog, yeah, options. Go. So if you have the options dialog selected under formula, you have R1C1. It's not really Excel, it was Quattro, maybe that introduced that format. But if you have the R1C1, you notice how instead of saying A5, it says row, and then you either have a bracket. So let me, okay. So you can have a bracket. That means relative to my current position. So if it was without the square brackets, it would be the absolute row or column in that. So R is for row, C is for column. And that's why you cannot define a variable called only C or R, by the way, in the spreadsheet, because internally they are kept for keeping track of the row and the column. That's why if you want to define a variable that's called C or R, you need to put an underscore or something. Okay. But if you're not going to work with that format of formulas, then obviously using formula names is the next best thing. So if I go H left, okay, so we're going to on the prev. No, sorry, I must be under next because we must define it from that sheet. Okay? So the hydraulic head on the left of B103, it's B103 in both, right? B103, B103. So left is this one. And I will remove the dollar sign from the A103 because I wanted to be able to move with me. Now we add H right. Sorry. Again, what's this? Oh, okay. Add H left. Add. Okay, because we were so if I add H right must be C 103. If I add H up, it must be B102. And if I add H down, it must be B104. Okay, should save it. Did I keep everything as formulas? That took a long time. Oh, yes, everything is formulas. So, domain, okay. Let me define this, copy and paste as values, and I will do the same for next. Copy and paste as values, because you saw how long it took to define three variables, right? So that's the thing you have to keep in mind and keep as few permanently defined functions as possible. So even here, yes, I need all of it, but I will keep the first row intact. And from below the first row, I copy and paste so that even under domain, I now have just constant values. Okay, that will just use less resources in the long term. Just a wise thing to do. So now I have defined numbers. Okay. So I will now define my equation general. Um, oh, first I should define kx left and kx y. Right. So let's do that first of all. So I should make sure first that kx, I have the same row and column selected. B103, okay, looks decent. So I add kx left, and that will be, right, A103. Again, I remove the dollar sign. I want it to move, but it's a next neighbor, okay? So now I add, and I add kx right, and that will be C103. And now I add ky up. It will be ky B102. And add ky down, ky B104. Okay, catch me, let me know if you catch any mistake, but this is what I see right now. Okay, so kx and ky have their specified directions. You see where we're going from what we did in the past weeks, right? We're trying to go and slowly define our, yeah, summarize. So now the general equation, I will call it equation so that they're all together. If you start the name of the variable with something, then at least they will stick together. general, okay? And that is what we said before. It's kx left times h left uh, plus kx right times h right plus ky up times h up plus ky down times h down divided by kx left plus kx right plus ky up plus ky down. Right? Uh, Now we'll define boundary condition. No flow. Uh, no flow up. Okay. First, actually, we should go from equation. Actually, equation. No flow. Uh, up. So what changes when you have no flow up? You have a mirror. So we have whatever is up goes down. So ky down times h down. Ky down instead of up, right? Okay. Um, and if we add equation, no flow, did I say up, left? That's the corner. It will be the same, except that left also becomes right. So that's right, and left becomes right. So we want to define all the basic equations that we will need to replace at the boundaries at this stage. And again, remember, you save this spreadsheet. Right now, we're building it from scratch, but if you save the spreadsheet, you have these equations. They will always be the same equations for steady state. So it will make your life so much easier every time that you work on it in the future. Okay. So we did up and up left. Now we can do the left. We'll start from the general. We have equation no flow. Um, no flow left. Right? And that means that left becomes right, left becomes right, left becomes right. And then we have equation no flow down. And then all down becomes up. Down becomes up. And then we have equation no flow down left. So every left becomes right, right, and right, and every down becomes up, up, and up. Okay. I would say okay and save. It's a good practice to save periodically. So we've done the left side. All we need to do is right and upright, down right for the no flow, at least. Equation, no flow, right as the general. So all the right becomes left. One, two, and there's always three of those to change. All the right becomes left. Eh? And what else did we have? Up left and bottom left. So we add equation no flow up right. So all the up becomes down, down, down. And all the right becomes left. So left, left, and left. And what's missing? What's missing? Uh, down, down right. No flow, down right. So all the down become up, 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 and all the right becomes left, left, left. Okay, we're done with the no flow boundary conditions. We need constant head upstream, constant head downstream. And and then we need no flow boundary, not no flow, but potential seepage phase. Okay? So we have equation, constant head upstream. And here we actually let's define variable because here we may want to change constant head upstream so that it's easier to change and we can have functions if we need to at some point. We could change it also as a variable inside the variable, but here constant head downstream say 0. No, what was the height of the thing? Was 5 meters, and I forgot to check what was the that's 7.4. Say 5 meters for the head of right now. We're gonna assume that that's the value, but we'll I forgot to mark it, right? Let's go to the CAD file. Uh, boundary. If I measure the distance, we'll have uh, to make do, but 4.15 meters. Okay. There you go. um, okay, so actually we could have equation, constant head, upstream. Let's say 4.15 for now. And equation, constant head, downstream. Okay, so the elevation will be taken at ground level. Okay. Um, what else? What else? What else? Oh, we need to define this one will be 0. This one will be that plus delta y. And did I not define delta y? Variables. U. And that one can be delta x. Okay. So we're almost done here, and that we can do a selective search and replace. Oh, I'm missing the the delta z. So this one is 0. This one is that plus delta y. Okay. And this is that minus delta y. Okay. So here we have our elevation head. And I will just define that for now as z. I know, I call it y and z. I'm a terrible person. For now, z is defined everywhere, so z should be small. Okay, yeah, 0.5. Component one, perfect. So the Z is defined wherever we are. Okay. So we have defined successfully the value of Z. So uh, equation potential seepage phase. If we are okay, let's see what potential seepage phase conditions we have. We can have either on, so this one can be potential seepage phase, or this one can be a potential seepage phase, correct? So what would be the difference? So in both cases, what I do is uh, one would replace if the left one hydraulic conductivity on the previous is smaller than Z, right? It means that we have suction. And if we have suction, if the hydraulic head on the left has suction, it means that we have a no flow, right? So if we have no flow, this one should be no flow because this is a corner. It should be, here you see an example of three. It has neighbors on all sides, so it's a good node. So that's why I say three or four is general equation. One is top upright. So it would replace by upright, no flow upright, while two would be replaced by up, boundary no flow up. Okay, so that's why we need two different equations. Okay, we need equation potential seepage phase up. What did I say? Up left, no, up right. And here I say if H left is smaller than Z, then equation no flow up right. Right? Else, what did we say? So if, however, we have potential seepage phase, then we have the potential, the hydraulic potential there is equal to Z. So it means that if there's any excess pressure, it can come through. Okay, so the whichever condition is met. Okay, sounds good. And we add equation potential seepage phase up, and I say if hydraulic conductivity, the hydraulic head on the left side is smaller than Z, I have equation no flow. Equation no flow equation no flow up, right? Otherwise, we have Z. Okay. Um, and maybe if we want to automate something more, we can say, because here on the left side, we can have what we will have will we have in terms of boundary conditions.
Professor,
Yeah.
uh, I want to know what would happen if we do not define any potential seepage plane.
The well, if you have no flow, um, it will force your flow to follow the boundary instead of having, so it will change the shape of your potential seepage phase. See? Oops. Let me try to illustrate it. So let's say that you have a boundary. Yeah, I guess we can do that. Okay. Convert to curve. Okay, so we have a boundary like this. If we say that we have, so you see what we have in this area here, okay, is a seepage through, right? We've been able to cut through. If we say it's a no flow boundary, we can no longer have that. So we must have now something like this, right? So it will change, it will potentially change the shape, of the well, it might not be like that there. Okay, can I turn it? Yeah. So it will change the nature of the flow lines. Okay, and that's why we need to have a potential seepage phase. By having a potential seepage phase, you're allowing water to seep through. I mean, technically, what it will happen is it will tend to follow, the edge there, but it really makes a difference into how it can potentially flow. Okay, that's why we define a potential seepage phase. Now, the other problem we have here is that we do have upstream constant head boundary condition along that blue line, right? But above that, say from here, definitely this part here, okay, that part there will be no flow. It is a potential seepage phase if we want, but really it's going to be a no flow because the water is below it. And the direction of the gradient means that it will tend to go in the direction of the flow. So it will go that way. It will never kind of loop back above there. So it's safer to just say, well, that one will be a gradient. So what did we do here? We did define a variable, constant head upstream, um, which will be equal to, so if we look at our named variables, we have constant head upstream. So let's add a boundary here, which is the one we will use, equation boundary condition upstream. And what we will see upstream, again, here we have a left and an up left because we can have one or two in terms of our boundary nodes. Okay, so one will be a corner up left, and the other one will be just up. So upstream, we have up left. Okay. And here we say if Z is larger than equation constant head, what was it? Equation constant head upstream. Then we have no flow. So we have equation no flow up left. Otherwise, we have equation constant head upstream. Sounds good? And if we have the 2 instead of 1, we replace it with equation boundary condition upstream just up. And that one is if Z is larger than equation constant head upstream. Then what we have is an equation no flow up only. Otherwise, we have equation constant head upstream. Okay, sounds good till there. So the only thing, so ideally this sheet I will save and have it forever. So all these variables for boundary, the different types of boundary conditions I can have, they would be essentially saved forever. The only one I might need to change, and this why I can choose to assign equation constant head upstream and downstream to a cell name instead, so that I don't have to go to manage names and just change the number in the spreadsheet, right? So this one, yeah, I could just refer them to these. So I could say that this is this, right? That one is that. Okay, so that it's easy to change just from the spreadsheet when once you work on the sheet. But the important thing is that now these can easily be changed. So you can say, you can select by areas, right? I mean, the bigger the image, the harder it is. So we went a bit ambitious here. Apparently. But see, I can just do so we can go by little chunks too. But because ideally what you want to do is, let's see, can I? So if I wanted to change my constant heads, right? I would come from here. I don't want to go all the way in. but I can definitely go to, oh, not, I want to stay on the upstream. Okay. So I can select all this area. Okay. And I can do a search and replace. Okay. I can do search and replace, replace two. Well, if I go up, because I can make it easy for the twos that are on the bottom. But I can basically change this by, I say search and replace find two, entire cell, and replace by equation. What did we call? Oh no, we called it the, okay, let's see first what we called it. Equation, boundary condition of stream. So two would be up. Sorry. So we replace, search and replace. Oops. It's not showing on the video. Let me fix that. Now we're on the spreadsheet. Office. Okay. I'm just adding a window. And that one will be find and replace. Okay. Okay, so we're replacing the text, which is two, and we replace it by the function, we say replace all within the selection. So current selection only, replace all. Okay. Oops, I forgot something. It's okay, we made a mistake. We undo, we redo, we say equal to that. Now we say replace all. So you see, I have made a replacement there, and because I have fours on the other side, that's where it changes. Okay, so replace two by equal, because I wanted to make it a formula, replace all, and replace one by, what did we want to replace it? Up left. But we want to replace within the same range, so I will go up. Move this to where we wanted to make the replacement. Okay, up to here. Up left, boundary condition, up left. Okay. So we made the change to all the equations. You see how easy it was? So I will do the same thing. I'll post this one. Yeah, we're almost out of time for today. What I will do is I'll post the spreadsheet to let you play with it and finish it by next time, and run the macro if you can. And we'll finish it together also next time. I'll see what we get as a result. Okay, but you see that once this is done, okay, it took way longer than it would take you in a normal operation because I have my spreadsheet already done. So if I keep the spreadsheet forever and ever, I could have done this in 10, 20 minutes tops because the real, well, once I have my image, say tracing the image, and that's another operation. But doing this is just import the image, copy, get the KC, you have your material map sheet that is calculated automatically, and bang, you can just generate these, do a quick copy and replace these for the proper equations. What took us time really was to define these equations, and I mean, we go through the step one at a time. But once you know how you set this up, I say from the image to this, 20 minutes is not too far-fetched to say that you got it set up, and now you run your uh, your session, right? And the beautiful beauty with this, let's say you use, instead of steady state, you have a time dependent formulation, like for your general formula. You could have a time dependent here also change in the upstream condition, right? You can have something set up to the specific time and date and have a pointer that increments. So you can become even fancier with these things based on your on the setup that you have. Okay. Anyways, we'll leave it at this for now. I will save it. Make sure that I save it. I will upload this to Brightspace, and this way you can play with it and keep the search and replace for next time. See if you get all the boundaries that you need, and we'll compare what you get next time. Sounds like a plan? And you will see we went through a big image this time. So, well, we should get a nice and exciting boundary condition problem. But basically, this is what you're paying the big bucks for those fancy softwares, for converting geometry by not making a matrix and just keeping the nodes and using the techniques that are like the explicit here. We're not using explicit finite difference, but because we're doing steady state, but we're still using the same principles for iterative solutions instead of building a matrix. Can you imagine the size of the matrix we would need for this one? Anyways, so you are free to ask any questions if you have one. And if not, let me start the upload procedure right now so that it's definitely in the proper class.
Professor,
Yes.
uh, I want to confirm when will be the presentation.
So not next Wednesday, the following one, right? Is that correct? The last class is the third, right?
The last,
Yes.
you mean the December the 1st?
The third, yes.
Okay.
So we do the presentation on the third. And
At
then
night or
Uh, let's keep the schedule as it is because I mean it will be online. It will be like we're doing it right now. So we don't have to go physically in class for it.
Because
And
I have another presentation
oh, you
at
do?
first, but it is in the morning.
Oh, it's in the morning. Okay. So yes, you can be wherever it's more convenient. So I like to do it online in case there's people who are not in the country. It's in the past it was an issue sometimes. So and that way after the presentation, you know, you could, if you did it from home, you could be at home already. So that's the it's the general idea.
Okay.
Okay.
Yeah.
Well, I hope you enjoyed that little demonstration. And again, once you run the outcome and you have a final solution, it's always much more fun. This is the beginning. Once you do the search and replace is the easy part now. Then you have to put some initial values on the previous if you want. Um, but again, 4 is not a bad because we had 4.15, so it's not actually a bad value to have because of the specifics of our of our boundary of upstream boundary condition. But yeah, we'll see next time what we get, and hopefully we get a nice, meaningful uh, phreatic line. See you all next week. Hopefully there will be no issue and I will be able to be on campus. I'm sorry again for that. It's never fun to have to change things last minute. But I should have asked you guys to have your cameras on while we did the presentation because I miss seeing your faces when I do the presentation. It's very depressing to be at home like this by yourself doing a class. Hopefully you were not too bored. Have a good week. Yeah, have a good rest of the week, and I'll see you next week.
See you, Professor.
Space, spread, space, spread, space, space. Damn model.